So in our last class we have seen the concept of symmetry, and with the help of symmetry we can easily solve the question, and we talk about input output symmetry and folding symmetry. So this is just a recap. So input output symmetry, what I told, look at this circuit. So all capacitors are of capacitance C, and if all are of capacitance C, then whatever I see from this side, same thing I can see from other side, right. So when I try to enter into the circuit from this side, I will see the same thing what I am observing while entering from this side, right. So this type of symmetry is called input output symmetry, and in input output symmetry we talk about the charge division, how charge will get divided. So in this example I told you, whatever is delivered to this one, same will be delivered back by this one, right, and whatever delivered to this branch, same will be delivered back by this branch, right, if it is connected to source this way. So if this is the situation I told you here, as this charge is same as this charge, that means there is no division here. I can just open this junction and I can redraw the circuit like this, right. When I open this junction, these two will become series, parallel, and then this whole thing will be series, and then the whole thing will be in parallel with this branch, right. So now I can simplify the circuit, I can see series parallel combination, it's easy to solve the circuit, right. So this is what we have discussed in input output symmetry. Our focus was on the distribution of charge, how charge is getting distributed. Then we talk about folding symmetry. What was folding symmetry? I took this example, and I already told a circuit can have more than one symmetry. Like in this case, this circuit is having input output symmetry as well as folding symmetry. What is folding symmetry? If I connect battery like this, so across this AB, if I look at the circuit, then whatever I am getting above, same thing I am getting below, right. So whatever I see above this line, same I see below this line, that means whatever given to this one, let it be Q1, same will be given to this one Q2. So as there is folding symmetry, these two charges are same, I can write here Q1, right. If this is Q1, both the capacitance are same, C and C, Q is equal to CV, right. That means potential difference here is same as potential difference here. So if potential difference here is same as potential difference here, this junction and this junction, they will be at the same potential, right. And when I look at this side, whatever is flowing through this one, same will be flowing through this one, because this is having folding symmetry. And again I can use the same concept, because this capacitor is same as this capacitor, the potential drop here will be same as potential drop here. If this drop is same as this drop, the potential here and here will be same. So these two will have, this junction and this junction, they will have same potential, right. So up to this point we have discussed in the last class, and I asked you to solve this problem using this concept, and let us see the solution. So first I will draw a simple circuit. So all are of capacitance C, right. What we will do, we start naming the junction, and when our circuit was having a conducting wire, there we discussed that 2 points having same potential can be considered as single point, right. So, as in this situation, here and here we have same potential, I can represent them by same point. For example, this is D, this is D, right. This terminal, let us name it C, and this one and this one, let this be A, B, C, D, let us call it E, 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 right. And now we will try to redraw the circuit representing these two by a single point D. Similarly, single point E. Let us draw. So, I need to reach from A to B, and in between there are terminal D or junction D, then junction E, and then junction C, right. So, these are the junctions we are getting in the circuit, and we are representing these two by single point D and these two by single point E, because they are at same potential, right. So, now let us connect capacitor in between and see whether we are getting simplified circuit or not. So, between AD there are two capacitors. Between AD there are two capacitors, right. So, this one over, this one over, this one over. Now, between AC there is one capacitor, between A and C there is one capacitor. So, this one is also over. Between DC, between this DC and DC, again there are two capacitors. So, I will draw it this way. So, these two also over, this one over, this already we have connected. Now, similarly between BE and BE there are two capacitors, BE and this BE there are two capacitors. So, this one over and this one over. Then between CB there is one capacitor which I connected here. So, this one over. CE and CE and this CE, there are two capacitors, those we have connected over. Now comes DE and DE. Between DE there are two capacitors, right. So, one capacitor here and one more capacitor over here. So, this is what we are getting. As you can see that these two are connected in parallel, these two are connected in parallel, parallel. So, 2C, 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 and this is 2C, right. And look at the circuit. Now, I can see that circuit has got, because directly after simplifying I am directly connecting 2C over here, right. So, in the diagram only I will make change, I hope you are understanding. So, here I will remove these two and I connect a single capacitor 2C, right. So, a single capacitor 2C. Then these two will also become 2C, right. These two will become 2C, these two will become 2C, right. So, here I will place a capacitor 2C, another capacitor 2C, and again we have parallel combination over here, then these two can also be reduced. connecting 2C over here. Now this is what maximum we can do after simplifying this diagram. We have done that, we got parallel combination, we connected capacitor in parallel combination. Now as we can see, there is input output symmetry. Whatever I am getting from this side, same thing I am getting from this side. So there is input output symmetry. That means whatever charge given to this, let us say Q1, that will be given back by this branch Q1, and whatever given to this one, that is Q2, that will be given back by this Q2. And from here till here you can see there is one junction. So if this charge is equal to this charge, that means there should not be any division of charge here at this junction. So this charge will completely flow this way, then only this one can be equal to this one, right. That means here I can open this junction. Once I open the junction, look at the circuit again. Now I can open the junction, it is something like this, right. Now I can further simplify the circuit. This will become C, series combination C, and then 2C in parallel. So this all together this will become 3C, right. This will become 3C. This 3C and this 2C will again become C, 3C, and that C will be in parallel, sorry, will be in series. Again look at this one, this is 3C, right. I am talking about this one. This whole thing is 3C, right. This 3C, this 2C and this 2C, they all are in series combination. This 2C and this 2C, I can make it C because they are in series. So what I can see, that C, this combination C and this 3C, they are in series combination. For series combination, C1 C2 upon C1 plus C2. So I can write C into 3C divided by C plus 3C, that is 3C by 4. So the upper branch, whole upper branch can be replaced by single capacitor of capacitance 3C by 4. Now comes this lower branch. These two are connected in series, capacitance will become C by 2, right. So this will become C by 2. Now these two are connected in parallel. If they are connected in parallel, I can add capacitance. So 3C by 4 plus C by 2 multiply and divide by 2 here, I can see 5C by 4. So equivalent capacitance of this circuit is 5C by 4, right. So you use the concept of folding symmetry and you solve the circuit using folding symmetry, and you are getting 5C by 4, right. As I already told you, circuit may have more than one symmetry. As we can see, this circuit is having input output symmetry as well. So if I solve the whole problem by input output symmetry, what I need to do here, whatever charge flowing through this one, let's first clear this. So I will clear all and we will check what we are getting if we start solving problem by input output symmetry. So input output symmetry, I will open this junction, right, because whatever flowing here will directly follow this path, what goes here comes out, so there should not be any division. Similarly here, what goes here delivered back by that branch. So this upper one, this whole thing, look at this whole thing, this will have capacitance, you can directly check, this is CC. So series combination this will become, because Now we are drawing this way. So C by 2, right? C by 2 and C, they will be in parallel, 3C by 2. So this whole thing will be 3C by 2. 3C by 2 and C by 2, they are in series. So 3C by 2 and this C by 2, they are in series. So let us first calculate what we are getting. Right. So if I simplify, then what I am getting here for this upper branch, this whole thing is 3C by 4, right, divide by 2C. This is what? 2C, right. So 2 will come and this will become 8. So 3C by 8 for upper branch. Similarly, you are going to get 3C by 8 for this lower branch. They are connected in parallel. So adding these two will give you 4C by, adding these two will give you 3C by 4. 3C by 4 and then C by 2 will come in parallel. So what I need to write? 3C by 4 and then plus C by 2, this one, right. If I simplify this one, then multiply and divide by 2, what you are getting? 5C by 4. So previous method gave me 5C by 4, and if I directly go by input output symmetry in this situation, I am getting 5C by 4. As you can see, in previous case I have to redraw the circuit, then I cannot further reduce the circuit. I need to apply concept of input output symmetry again, and then we start reducing and we got this answer, right. But if we go by input output symmetry, in one go we directly got the answer. So which problem should be solved by input output symmetry and what problem should be solved by folding symmetry, that comes from practice. So slowly once you have practice, then you will realize that a particular type of problem can be easily solved by input output symmetry or by folding symmetry. So I hope the concept of input output symmetry and folding symmetry both are clear, right. So folding symmetry we discuss and input output symmetry we have discussed. Now we will take some examples so that we can clearly understand the concept. So I will take few more examples. Let us take this one. So across AB I need to find out capacitance, right. If I solve it by input output symmetry, because I can see there is input output symmetry, whatever circuit I am seeing from this side, same circuit I am seeing from this side, and there exists folding symmetry as well. So about AB, whatever I see this side, same thing I will see on other side. So circuit is having input output as well as folding symmetry. Let us solve this problem by both the method. So input output symmetry, if I apply, now see, whatever charge given to this one, that will be given back by this one, whatever charge given to this one, that will be given back by this one. So if this charge is same as this charge, there is no role of this capacitor. If this charge is same as this charge, that means there is no division, there is no role of this capacitor. So I can remove these two capacitor and redraw circuit this way, right. Removing these two capacitor, I can redraw circuit this way. After redrawing circuit, I can easily see what is happening. 2C and this 2C, they are connected in series. So C I can see here, C, C, and then it will make it 3C, right. So capacitance equivalent will become 3C. So this is method 1, right. And if I solve it by, so previous one is input output, now we want to solve it by folding symmetry. So, we have already solved by input output. Now, folding symmetry method, let us check what we are getting. As I am going to connect battery across AB, about this line I can see symmetry. If about this line I can see symmetry, that means the point above this line and point below this line, these two will be at same potential, right. So, let us name them as D, okay, and the junction here let it be C. So, from A to B passing through C and D. So, let us draw it A to B passing through C and D. So, I will draw it C and D, right. So, I have selected point this way. Between AC, this is 2C. Between AD, 1 2C here, and between AD I can see one more 2C, right. And then between DB, one capacitor 2C and DB there is one more capacitor. So, this 2C and this 2C, so this one and this one over AD, these two over AC, this one also over, right, and then CD and CD, there are two capacitors. So, here I can draw two capacitor, one this way, another this way, right. This one. So, these two also over, this over, this over. Between BD, B and D, these two also over, two capacitor I have connected here. Now, what is left is CB, this capacitor is left. So, I will connect and its capacitance is 2C. Now, circuit looks little complicated, but when you simplify, this will make it 4C, right. So, here we have 4C, this is 2C, and again this will become 4C, parallel combination. This will become 4C. Now, we cannot further reduce the circuit because now nothing is in series and parallel combination, but what I can see that this one upon this one is equal to this one upon this one. As this one upon this one is equal to this one upon this one, this is a balanced Wheatstone bridge, right. And if it is a balanced Wheatstone bridge, there is no charge flowing through this branch. So, as there is no flow of charge through this branch, I can remove this capacitor, I can remove this capacitor, right. There is no flow of charge through this branch. Last class we have seen this concept, balanced Wheatstone bridge. Now, when I remove this, so when I remove this, then I can see these two are in series, these two are in series, then they are in parallel. So, 2C, 2C they are in series, it will make it C, and 4C in series, it will make it 2C. Right, and C equivalent we are getting 3C. This is what we got when we solve the same problem by input output method. Method 1 we got 3C, again we are getting 3C. So previous case I can straight away eliminate it. If you see, I straight away eliminated this one and this one. I divided charge, and from there I came to know that there is no use of these two capacitor, and I reduced the circuit. So in one step I got answer. While if you look at this one, if I go by folding symmetry, I will have to redraw the circuit. After redrawing the circuit, we got Wheatstone bridge. Those two capacitor we eliminated in the previous case, same two capacitor we are eliminating in this case also, right. So no matter whatever way you want to solve the problem, the capacitor which are inactive in the circuit will remain same, right. So simplifying this one, again we got 3C, right. So I discussed this method to make you understand, irrespective of the method you follow, you are going to get the same answer. The only thing, the time taken by problem to solve by one method might be different to the time taken to solve the problem by another method. So with little practice, you can easily understand which method should be followed in what particular type of problem, right. So let's see few more example. Look at this one. Again this is having folding as well as input output symmetry, and if I solve this problem by input output symmetry, I can easily get the answer. How? So this complete thing will become C, this complete thing will be C, right, and this charge must be equal to this charge must be equal to this charge. If this charge is equal to this charge, that means there should not be any division here. I can separately draw them, or I can say we can open this junction. Now after opening this junction, I can see these two are in series. So here C and here C by 2, here C and here C by 2, let us draw it. So this one is C and this one is C by 2. Then this one is 2C, this one is 2C. Right, and same you are going to get for this below part of the circuit, 2C, this one will be C and this one will be C by 2, right. So C by 2, two C, now we can see that all the capacitor came in series parallel combination. I can further reduce it, right. So here this will become 3C by 2, C plus C by 2, similarly 3C by 2, right, and these two in series combination they will become C. So C and 3C by 2 in series, C and 3C by 2 in series. So for upper part, capacitance of upper part is this 2 and 2 will get cancelled out, we are getting 3C by 5. So upper part 3C by 5 and lower part 3C by 5. So, capacitance of this arrangement will become, these two are in parallel combination, capacitance will become 6C by 5, right. This is when we are solving problem by input output symmetry. So, method 1, input output, right. You can also solve this problem by folding symmetry. Let us see. So, I hope this whole thing is clear. Now, for folding symmetry, how to draw the circuit, we are getting 6C by 5. Now, for folding symmetry, I can see about this line, circuit is symmetric. So, whatever be the potential here, this I can reduce, right. So, this I can reduce and I can make it C, and similarly here this I can reduce and I can make it C. So, after making it C, this potential and this potential, they will be same, this one and this one will be same, right. So, let us name them. So, this is D, D, E, E, and let this be C. Okay, let us check whether we are getting same result or not. So, A to B we need to reach, A to B, and in between we have D, D, C, E. Between AD, between AD, there are two capacitors. So, I can draw 2C, 2C, right. So, I have drawn these capacitor, I will draw cross mark so that we will not get confused. Between DC and DC, again there are two capacitors. So, C here and again C here, right. These two are having capacitance C. So, this part is also over now. So, these two over. Similarly, these two I will connect here, this is C and one more capacitor C. Two C and 2C. So, here 2C, here 2C, right. So, what is left? Between D and E, one C, between D and E, another C. So, D and E, here one capacitor of capacitance C combination and one more capacitor of capacitance C in combination. So, now I can see 4C, 2C, 2C, 4C. Let us draw it again separately. So, between AD I can see 4C, between DC 2C, between C again 2C, between EB 4C, and then these two 2C, right. So, between D and E I can draw 2C. Now this is our simplified circuit. Everything is coming in series parallel combination. We can further reduce it and get the answer. So these two will make it C, C and 2C connected in parallel. So we'll make it 3C. So this whole thing will be 3C, right? So this whole thing is 3C, and then this 4C, 4C, they are connected in series. So it will make it 2C, right? I am directly drawing. So we got this one. Two capacitor connected in series, C1 C2 upon C1 plus C2. So by method 1 we got 5C by 6C by 5, and by method 2 is folding symmetry method, right? So by folding symmetry method we are getting same result. So we have solved the same problem by both the method, we are getting same result, right? Now let us move to next example. Look at this circuit, and you need to find out capacitance across AB, right? So what would be the capacitance of the circuit across AB? What type of symmetry the circuit is having? So you can see it is having folding as well as input output symmetry. If I join A to B, I will be getting this line like this. So this is having folding as well as input output symmetry. Folding, so we can clearly see about this line, whatever you are getting on this side, same thing you are getting on other side. So folding easily we can see. Let's see input output symmetry. So input output symmetry. When you try to enter from A, then you are seeing 2C this way and C which is directly going to output. When you try to enter from B, then you are seeing this C going directly to A, and this side 2C and this side 2C. So this circuit is having input output symmetry as well as folding symmetry. If I try to solve this by folding symmetry, first I will try to solve it by folding symmetry. So method 1, folding symmetry. So as the circuit is symmetric about this line, the potential this side will be same as potential here. Similarly, the potential here will be same as potential here, symmetric points, right? So let us start naming junction. So A, B, let us call it C. If this is C, this will be C, and if this is D, this will be D, right? So A to B through C and D, right? Through C and D. So C and D. So I think it will take more space. Let us draw it here. From A to B, then we have C and we have D. Okay, you can also draw on a straight line, right. So by practice you will get idea how to take points in a space so that two elements never overlap. If you just draw always on a straight line, it might be possible that two circuit elements will be overlapping, and then it will be very difficult to decide which one in series and which one in parallel. So I am drawing it this way so that I won't get any overlap. Let's see. So C and C, from B to C, there are two capacitors, 2C and 2C. So here I will write 2C and then one more 2C. Okay, these two over. Between A and D, between AD, there are again two capacitors, 2C and 2C. This is also over. So these two over. Between A and B, there is one C. So between A and B there is C, right. So this one over. Okay, and then between C and D, there are two capacitors. Now you can see the problem what I was telling, that if I connect something in between these two, then they will overlap, right. So when you start seeing any overlap, again redraw the circuit. So I took 4 random points this way. Now what I will do, as I can see overlap, circuit will become complicated. So I will draw, or I will try to draw another circuit taking them on a straight line. I hope you understood the point what I was telling. So if you see any overlap, redraw the circuit by taking point at the different locations. So now as I was getting overlap, I will draw the circuit taking all the point on the same line, right. So A, B and C, D, right. Why I am not drawing A, C, D, B? Because A is directly connected to D by a single capacitor. So there will be a single capacitor over here, that is why I have taken D near to A and I have taken C near to B. Now it is time to connect the capacitor. AD, I can see one capacitor over here and another capacitor over here. So 2 capacitor, right. So 2C and then one more 2C, right. This is over. So AD over BC, BC, 2C, these two over. So this over, this one over, right. Between CD there is one capacitor here and one capacitor here. So C and C there are two capacitors. So this one, C and C, right. What is left? Between AB we have a single capacitor which is directly connecting A to B, okay. So AB we have a single capacitor C, this one also over. Now comes this 2C and this 2C. As potential here and here they are same, there is no role of this capacitor and this capacitor because charge flows through potential difference. As difference is not there, there is no role of this capacitor. So I can remove this capacitor I can remove this capacitor, right. Between D and D one capacitor is connected. As there is no potential difference, these two are at the same potential. From folding symmetry I can say no role of these two capacitor. So, I will remove those two capacitor. This is the circuit what I am getting. We can simplify. Here I can see 4C, 2C and 4C. This 4C will make it 2C, 2C and this 2C will make it C, C and this C parallel combination I can see 2C. So, C equivalent I can see 2C. This is by folding symmetry method, right. So, I hope this is clear. Two terminals having same potential replaced by single point and then we simplified the circuit, right. If I want to solve this problem by input output symmetry, right, the method input output symmetry, whatever be the charge flowing here that will directly reach to B. We are going to connect battery across AB. If you are asked to find out capacitance between AB, that means battery is going to be connected across AB. So, this charge will directly flow, right. Whatever given to this branch will be given back by this branch, symmetry. Similarly, whatever given to this branch will be given back by this branch. So, if this charge is same as this charge, that means charge will be flowing like this, charge will be flowing like this here. Similarly, this charge will be flowing like this. If this charge is flowing this way and this charge is flowing this way, that means no charge is entering into this capacitor and no charge is entering into this capacitor. Here there is no division, here there is no division, no charge is flowing through this capacitor, this capacitor. So, by folding symmetry we also got the same analysis that these two are not useful capacitors. We can remove these two capacitors. As we remove these two capacitors, I can redraw the circuit this way after removing this one and this one. Now, after removing these two, here look at this one, these all will come in series. Similarly, these all will come in series. What is the capacitance of this part? This 2C connected in series, it will become C. Then this C along with this C, this will become C by 2. This is becoming C by 2 and this is becoming C by 2. C by 2 here, C by 2 here, parallel it will make it C and one more C is there, then it will become 2C, right. So, I can further simplify AB I am drawing here, this capacitor here, this whole branch is C by 2 and this whole branch is C by 2. Now, all three are connected in parallel, you will get capacitance 2C. So, previous method we got 2C and this method we are getting 2C. So, we have discussed almost 3 problems, right, where I proved that no matter whatever procedure you follow, you are going to get the same answer, and this is the simplest method of solving the problem, because if circuit is having symmetry, we can easily remove capacitor, or we can decide which capacitor in the circuit are not useful, we can remove them and we can calculate capacitance, or by this method we can decide whether there is any distribution at the junction. If there is no distribution at the junction, we can open the junction and we can reduce the circuit, right. Now, let us see another example. So, 12 arms or 12 edges of a cube, we have capacitors connected. So, altogether there are 12 capacitor connected, and we are interested in calculating capacitance across, according to the question, between the diagonally opposite corner AB. So, across these two I want to find out the equivalent capacitance, right. So, there are n number of ways of solving this problem. So, if I go by charge distribution, simple charge distribution, if I see, that is nothing but input output symmetry. What I see from this side, same I am seeing from other side, right. So, if I start distributing charge, let when we connect battery, V volt battery, the charge given by the battery is Q. So, battery here delivers Q charge, right, and we are interested in calculating AB, right. So, it is connected to B, right, not D. As across AB I can see input output symmetry, whatever is charge given to this branch will be given by this branch, whatever charge given to this branch, that will be given by this branch, whatever charge given to this branch, that will be given back by this branch. As all these branches are similar, that means here charge will get equally divided into 3 parts. So, charge flowing through this one will be Q by 3, charge flowing through this one is Q by 3, charge flowing through this one is Q by 3, right. Once this Q by 3 reaches here, or this Q by 3 reaches here, then we can see there are 2 paths available and both are similar paths, right, both are similar paths. So, this charge will further get divided into 2 parts, this is Q by 3 will get divided into 2 parts, Q by 6, and this will be Q by 6, right. So, this Q by 6, this Q by 6, and you can see that this has to be Q by 3, right. Whatever given to this branch, same will be given to this branch, given by this branch, because there is input output symmetry. So, if this is Q by 3, this charge has to be Q by 3. So, if this is Q by 6, this is Q by 3, that means Q by 6 will be coming through this one, this Q by 6 and Q by 6 will make it Q by 3, right. So, you can select any of the branch, I have selected this branch, right. So, I will draw line so that you can visualize which branch I am talking about. So, I am talking about this branch. What I say that you can select any of the branch, right, it does not make any difference. So, if I apply Kirchhoff voltage law across this one, right. So, what we can write, V is equal to so this simplified diagram I will draw here. So, I have taken this branch, now I hope now it is clear. So, we are going to apply Kirchhoff voltage law across this. So, this V voltage must be equal to voltage drop here plus voltage drop here plus voltage drop here. So, V is equal to Q is equal to CV, right. Q is equal to CV, V is equal to Q by C. So, for this one I can write Q by 3C plus this capacitor, it carries charge q by 6. So, here I can write q by 6C, right, plus here this carries charge q by 3 and the capacitance of this one is C, right. If I add all these terms, so multiply and divide by 2 here, this all will become 6, 2 plus 1, 5 q by 6C, right. Now, what's the meaning of that? Capacitance equivalent procedure was we give charge and we get the potential difference. The ratio is called capacitance, right. We discuss spherical capacitor, parallel plate capacitance, right, and cylindrical capacitance. So, in all these cases what we have done, we gave q charge through potential difference V, whatever was the ratio, that was q equivalent. So, here same thing, we are connecting V volt battery and we are assuming that battery gives q charge. This ratio must give me capacitance. What is this ratio? If I simplify, I can write 6C by 5 must be equal to q by V. So, this what we are getting on other side must represent the capacitance. So, this must represent the capacitance. Capacitance of the arrangement will be 6C by 5, 6C by 5, right. So, we just distributed charge using symmetry, input output symmetry. Here we are not getting any inactive capacitor, we are not getting any junction through which charge is not getting distributed. So, I cannot remove any capacitor, I cannot open any branch or I cannot open any junction, right. So, the only option left is just distribute the charge, apply Kirchhoff's law, and after applying Kirchhoff's law, try getting the relation between charge and potential difference, whatever be that ratio, that is the capacitance of the arrangement. So, in any circuit, if you are unable to reduce the circuit further, this is the procedure we follow, right. If you can reduce the circuit, you are getting series parallel combination, then directly you can simplify the circuit. If it is not possible to reduce the circuit, then this is the only option left, you connect V volt battery and then simplify, right. So, I hope this whole thing is clear. I use input output symmetry here. As the diagram is 3 dimensional, instead of plane of symmetry, you are getting line of symmetry. So, visualize a room about diagonal in the room, right. The whole thing I can say is symmetric. So, about the diagonal, if I draw diagonal joining A and B corners, diagonally opposite corner, if I join line, then I can see the whole thing is symmetric, right. So, I can solve this problem by that method also, right. So, let us see it by method 2. Method 1 we have discussed, I use input output symmetry. Now, method 2 using folding symmetry, right. So, method 2. So, folding symmetry. Here I am getting, if we are connecting battery across AB, right, we are connecting battery across AB, line joining AB, about that the whole circuit is symmetric, right. So, you have to visualize that joining A to this B, this line I am talking about. So, about this line the circuit is symmetric, right. So, all the points about this line they will have the same potential, right. Let us select those points. So, about this line I can see that this one and this over and this one, right, they are at the same potential, and then similarly this one and this one and this one they will be at the same potential, right. This is what I can see about AB I am talking about, right, about AB. So, battery is connected about AB this way. So, let us start. So, if this is D, this will be D and this will be D because they are all at the same potential, right. If this one is A, D and let this be C, if this is C, this is C and this is C, all will be at same potential, right. So, from A to B I need to reach A to B passing C and D, C and D. So, there will be 12 capacitor, I will make it little big so that there is no confusion. So, A to B, intermediate terminal C and then D, right. So, all 4 junctions we have drawn and then we start connecting capacitors, right. Look at these 3, A to C, A to C, A to C, right, A to C, A to C, A to C. So, 3 capacitors I will connect here, A to C, A to C and A to C, these 3 over. Then between B and D, again there are 3 capacitor I can see, B to D, B to D, B to D, right. So, here I can see B to D, this is B to D and this one is B to D. So, 6 over the remaining 6 between CD, between this CD, between CD, between CD. So, rest all are connected between CD. Through A there were 3 capacitor connected, we have already drawn. Through B there were 3 capacitor connected, we have drawn. So, rest out of 12 remaining 6 will be connected across CD. So, there will be 6 capacitors here, 1, 2, 3, 4, 5 and then the last one, 6th one, right. So, as these all are connected in series, I can directly take 6C here, 3C for this one, parallel combination, 3C for this one, parallel combination, right. Now, these capacitors are connected in series, 1 upon C equivalent will be equal to 1 upon 3C plus 1 upon 6C plus 1 upon 3C. So, multiply it, divide by 2, 2, 2 plus 2 plus 1, 5, 5 I can see, 5 by 6C, that is C equivalent. That means C equivalent will be 6C by 5. So, by distribution of charge using input output symmetry we got 6C by 5. Now, using folding symmetry, I am getting the same result, right. As the structure in 3 dimension, we are talking about the line of symmetry. So, about diagonal it was symmetric, and using concept of symmetry we solved this problem. So, here our focus was on the voltage division. All these 3 will have the same potential because they are similar for A. Similarly, when you are coming from B, these all, this one, they will be similar. So, here potential will be same, and then we reduce the circuit by mentioning them by drawing them to single point, and we simplified, we got the answer, right. So, now in the same question, if I ask across AD what would be the capacitance across these two. So, if I am asking across AD, then I want to connect battery this way, right. So, if I want to connect battery this way, input output symmetry, charge look at the circuit, right. This circuit will have input output symmetry, right. So, one point is here, another point is here. This circuit is having input output symmetry. Whatever given to this one Q1 given by this one Q1, whatever is this branch for this as input, same will be this branch when this is input, right. So, symmetric. And then look at these two paths. This will be equal to this one and this will be equal to this one, right. So, if this is equal to this one, this is equal to this one, that means there should not be any flow of charge, because this charge will directly go this way, there is no division here. Similarly, if this charge is equal to this charge, then there is no division over here and there is no use of this capacitor also. So, these two vertical capacitors we can remove and we can redraw the circuit. So, I will remove the battery. This is just to make you understand how we are connecting the source, right. So, this can be drawn this way, removing these two capacitor, removing this capacitor and back one, I will be left with this circuit. Now, look at the upper part, these two are in series C by 2, these two are in series C by 2. So, C by 2 and C by 2, this C by 2 I have drawn here, this C by 2 I have drawn here, this C and this C is over here. Similarly, this one, lower one is C by 2 and this one is C by 2. This way the circuit can be reduced. Now, these two will make it C and these two will make it C, and this one left, which I will connect here. Now, these all are in series, so C by 3. So, C by 3 I have connected here and this C here. Now, these two are in parallel combination, I can write 4C by 3. So, here we use concept of input output symmetry and we got 4C by 3, right. Is there any other kind of symmetry in the circuit? Through C and D, visualize, through C and D you can pass a plane, through A and D you can pass a vertical plane, and about that vertical plane the circuit is symmetric. Whatever you are getting this side, same you will be getting on other side. Okay, let us draw another circuit, because in this circuit you won't understand, I will take it another circuit. Okay. So, now what I am saying is, if you focus on this one, I am talking about this plane. So, plane passing through diagonal of this face, because we are going to connect battery across AD, so we need to take a plane passing through this diagonal. So, about this diagonal I can see whatever I am getting on other side, same thing I am getting in front of the plane. That means the potential here and the potential here, they will be same. Similarly, the potential here and the potential here has to be same, right. So, these two red marks, they will have the same potential, and these two blue marks, they will have the same potential, right. So, now we need to simplify the circuit. So, we saw folding symmetry, about this plane, and what voltage we are getting here, same voltage will be here. These two can be represented by single point, right. So, across AD I want to find out, if I call it C, then this will be C, right, and if I call this one as E, this will be E, correct. I am getting one extra terminal, A, B, C, D, E, let us call it F. So, A to D I need to reach, C and E, and near to A there is F, this F, and near to D there is B, okay, and C is between F and B, and E is between A and D. So, I will draw C here, and to avoid confusion I will draw E over here, right. Now, let us start connecting capacitors. Between AF, I can see this capacitor, this over, then similarly between DB there is one capacitor, so this one is over, then between F and C there are two capacitors, F and C there are two capacitors, so this over and this over, between B and C there are two capacitors, between B and C there are two capacitors, right. So, these we have already connected. What all are left? AE, A to E, A to E. That is why I have drawn a point here, so that there is no overlap, and between D and E there are two capacitors. So, this one over, AE over, and D E. So, this one over and this one over, D E. So, D and E, right. So, if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2 capacitors are still left. Look at these vertical, this one CE, CE and CE, CE, CE and CE. Now I think you have much idea that this is a Wheatstone bridge where this one upon this one is equal to this one upon this one. This is 2C and C parallel. So, 2C by 3, right. Now I am directly drawing, this is 2C by 3, this whole thing 2C and C parallel combination. Similarly 2C by 3, this is 2C, this is 2C. This is again 2C. As you can see, this one upon this one is equal to this one upon this one. There is no role of this capacitor. I can remove this capacitor. This can be removed. When this is removed, these two will become series. So, here capacitance will become C by 3 and here capacitance will become C. So, upper one is C by 3 and lower one is C. Now, these two are connected in parallel, we are getting 4C by 3. So, previous case we got 4C by 3, look at this one 4C by 3 when we solved problem with input output. Now, we are getting again 4C by 3 when we solve problem by folding symmetry, and you can see that this plane I am talking about, and then there is a circuit, right. So, this is a diagonal plane. So, what we have back of the plane, same thing we have in front of plane. So, folding symmetry, these two will be at the same potential, these two will be at same potential. You can redraw the circuit and then you will come to know which two are in parallel and which are in series combination, you can reduce, right. So, I hope the whole concept of circuit symmetry is clear. Till now we talk about series parallel, we talk about the conducting wire, and then we talk about the Wheatstone bridge and circuit symmetry. So, next class we will take few more problem on circuit symmetry and we will take some problem related to the circuit, how to solve the circuit, how to find out the charge flowing, especially when switches are involved, right. So, I hope you enjoyed today's class. Thanks for watching.